when I was throwing something up in the air, we talked about that as well, how the initial velocity was right after it leaves my hand, and then the final velocity was right before it reaches my hand and stops again. The same will be true here. Now, our velocity in the y direction, and remember v naught y is equal to v naught times the sine of theta. This is my v naught y. It's going to follow the same path as we had for free fall motion. Remember with free fall motion, like if I take this and I throw it up and it comes back down again, the velocity in the y direction decreases as it goes up. It goes to 0, and then it increases, but in the negative direction. Exactly like what we were doing. In fact, as you're working through projectile motion problems, it'll be useful for you to separate the x and the y motion into two separate problems. All right, so we see here that initially Vy is big. At the top, Vy goes to 0, and then over here, Vy is big again, but in the negative direction. Let's just remember those basic ideas that we had for free fall motion. Or if we had something that went up and came back down again. You've written this down already, but let me just remind you for free fall motion that the velocity at the top is equal to 0. V naught down here is equal to the negative of V final over here. That it's going to have the same speed when it returns back to your hand. And then also the time required to go up is equal to the time required to go down. In fact, we'll see that the y motion of our projectile governs or tells how much time the object will be in the air. Not the x motion. Let me show you. Let me find something to throw. Alan, I'm going to throw this to you. Can you catch it? All right, so if I throw this to Alan and I have a shallow angle, that means it's not going to go very high. All right, so you ready? All right, throw it back. All right, so it didn't go very high, but what happens if I throw it with a big angle and it goes up high? Is it going to be in the air for a longer amount of time or a lesser amount of time? Longer, because it goes up higher. It's still going to the same point, but it's going to stay in the air a longer amount of time. You ready? I mean, you can see. Could you tell that it was in the air longer? All right. Sorry. Well, not very coordinated, not very athletic. But let me tell you a little story. You want to hear it? In my 151 class, we go over to the rec center on the last day because we talk about all this stuff, but it's like physics with no math. And so we go over to the rec center and we do like all sorts of stuff with energy and projectile motion and what have you. And one of the things is projectile motion is a free throw, right? That is projectile motion. When you take a basketball and you throw it up. And man, I'm terrible at basketball. I make about 1 out of 20 free throw shots. Y'all here? No, y'all are probably pretty good at it. But every time that I'm taking my class over there, I always tell them, it's like, I'm not very good at basketball, you know, but it's projectile motion. And I'll take them, it's like, just, you know, practice your free throw shot, and we talk about a few things. And I go up, and every time I brought them over there, I get nothing but net on the first go. Nothing. They think I'm the best basketball player in the world. They just think I'm making that junk up, that I'm not very good. But it is projectile motion, that you have something that's traveling in 2 dimensions, in both the x and the y direction. Let's listen, actually. We have a little clip. This is really just for your own information, but it's about what makes the best free throw shot. Yeah, here it is. This is a physics professor. He's probably not very good at basketball either, but he's done a lot of work into figuring out what is the best angle that you can get for a free throw shot. And in short, he finds that the best angle for a free throw shot is the angle that gives you the softest shot. That is the angle that gives you the slowest speed when it actually reaches the rim. So let's just listen to this, and so that you have them actually in your workbook. We have Logger Pro. If you want to use this software, I can give you a free copy of it. Just let me know. I've already set up my origin. I need to set the scale. I'm just going to use the dab to set the scale. He's a little under 2 meters, maybe he's 1.8 meters tall. Yeah, he's almost 6 foot tall. And then I'm going to go in, I'm going to pick out the ball. It's sort of hard to see right here, but the ball is right there. And then every time it advances 1 frame, I'll click on the ball. Notice that it's following that. If you can see the blue dots, it's following this sort of parabolic path. Also notice that at the top that the dots are getting really close together because the velocity, while the velocity in the x direction is constant, it does what at the top in the y direction? It goes to 0. But remember, the velocity in the x direction will remain constant. It's just you're losing that y component of the velocity. So it's still progressing forward, but just not up. And now it's beginning to come down again. All right, and then it hits the basketball goal. So this is the motions. The blue here is the displacement in the x and the y direction, and then the red is the displacement in the x direction. I'm just going to pull up the red. So if I pull up the x direction, notice that it's a straight line, so it has a constant positive velocity in the x direction. You will have some qualitative view of graphs again on this next test, just like we had on the previous test. So we'll see that again in the context of two-dimensional motion. And then if we pull up the y motion, or this is the y velocity, notice that it has a big positive slope here, it has a slower positive slope here, and then it has a 0 slope there. So it goes up decreasing and then comes down with a negatively increasing speed. We can look at the x velocity here, although it's mainly just scatter. And then the y velocity. This is a straight line. The slope of this line, if I were to plot it, or the slope of this line should be equal to, oh gosh, what should it be equal to? It should be equal to -10. It looks like I get it to be about -9, which is close. My scale is a little bit off. If I plot this, as we've seen already, if I plot the y velocity versus time, it's going to look like that. Right here is at the top of the trajectory. This is a big positive velocity. This is a big negative velocity. So you'll still see these displacement and velocity versus time graphs on the next test, and you'll see them as we go through with two-dimensional motion. It's a good honors project. If you want to do this for your honors project, you can visit a few sporting events on campus and video them, and then do some nice analysis of the motion of the balls or the players, whatever. All right. I'm sorry, give me just a minute. I don't know what's wrong here. I'm going to close it and reopen it. I'm sorry, just give me a moment. Sorry, folks. Get back on task here in just a second. Let's try some of these questions while we're waiting. These are in the back. Vectors are given such, oh, I'm sorry, we've already done that. A small cart is rolling at constant velocity on a fast track. It fires a ball straight up into the air as it moves. After it is fired, what happens to the ball? So what happens here is we have this cart. A cart, it's on a track. It's traveling in this direction. And then we have a ball that's fired straight up. And so what I want to know is, what happens to the ball after it's fired? Does it depend on how fast the cart is moving? Does the ball fall behind the cart? Does it fall in front of the cart? Does it fall right back into the cart? Or does the ball just remain at rest? What happens to the ball after it's fired straight up as this cart is moving in this direction? Think about what velocity the ball has as it's moving here, and then what happens to that velocity as the cart continues to move. And it falls right back. All right, many of you have the right answer, about 30 of you do not. So ask your neighbor again if you like, see what they put. I'm going to stop at 148. 148. All right, awesome. So these are sort of the most common answers, either B or D. It's pretty good, actually. Most people think that it's B, that it's going to fall behind the cart. But if the cart is moving at a constant velocity in this direction, that same velocity is going to be given to the cannonball. So, cannonball. So as I move it along, the pin has the same velocity as I have, and I throw it up, and it keeps traveling in the X direction, even though it also has this added Y component of velocity. So it still has the X velocity that I'm giving to it just from walking with it. See, it's moving like this. And then as I throw it up, it comes right back down into my hand. So D here is the right answer. You're just giving it a Y component of velocity, but the Y and the X are independent of one another. Now the cart is being pulled along by an external force. That means that it's going to be accelerating, and it fires a ball. After it is fired, what happens to the ball? And the track's not tilted, so it's not A. Does it fall behind, in front of, back into the cart, or does it remain at rest?
Straight up again.
You're shooting it straight up again, right?
So whenever the ball leaves the cart, everyone is one speed, but then the cart keeps accelerating and the ball doesn't. That's it, falls behind.
All right, feel free to ask your neighbor what they put. Oh, y'all doing really well. I'm going to stop at 108. 108. Okay, awesome. So it falls behind the cart because if you're walking along at a constant velocity, you're giving the pin the same velocity, or the cannonball or whatever, the same velocity as you have. But if after you throw it up in the air, then you speed up, then you're going to leave it behind. Because after it leaves your hand, it just has the velocity that you've given it. And then if you're increasing in velocity, then it'll fall behind you. Let's see if I can do this. So. All right. That's very good. Let's see if I can pull this one off. This one's kind of a complicated humor, so y'all might not think it's very funny. Not that you're not complicated people, you are. But it's really a joke about perspective. It's very useful for today. Snail goes to the doctor. He's like, I was in an accident and I got hurt. And the doctor's like, what happened? And he's like, well, this turtle ran into me. And man, I just don't know what happened. You don't get it. No. See, because the turtle moves slow, but the snail moves slower. And the snail thought that the turtle was moving really fast. Yeah. Which side of the chicken has the most feathers?
The outside.
The outside. See, that's more our speed, right? All right. Venus. You drop a package from a plane flying at a constant speed in a straight line without air resistance. The package will do what? So here's my plane. Here's my package. I drop the package out of the plane. What's going to happen to the package? Will it lag behind the plane, or remain vertically under the plane while falling, or move ahead of the plane while falling, or not fall at all? I gotta think about that. I'm going to pull up my thing again. There we go. All right, I'm going to stop at 105. 105. Just guess if you're not sure. Okay, good. It is going to remain vertically under the plane. As the plane travels along with a constant velocity, the object is also going to travel along with that constant velocity, but then it's also going to fall. So as the thing falls, the plane is going to remain directly overneath it, yes. Let's stop here. Or not stop. Well, let's go back to our example. This is a nice projectile motion problem. We'll watch this. I want you to think about, this is Gone in 60 Seconds. Y'all seen this movie? It's with Nicolas Cage. Somebody kidnaps his brother, I think his brother, and he has to go steal like a dozen cars or more in order to get his brother back, like really high-end cars. Don't steal things. In fact, what's my advice to you? Have I told you my advice? Don't go to jail. Like, that's good advice. Don't go to jail. If you can sort of pull that off, you're doing pretty well. But anyway, what happened? Nicolas Cage stole these cars, and in the end, he steals this Mustang Shelby GT, and he's being chased by the cops, and he comes to a traffic jam. But oh no, what's he gonna do? Oh wait, there's a ramp there, and he jumps the ramp, and he jumps over all the police, and it's like whoa. But it's actually a really good example of projectile motion and a nice example of the type of problems that we'll be working through. So let's watch it, and then I want you to think about what's all the information that we need to calculate both his horizontal range and his total speed at impact. So there's two pieces of information that we need in order to determine the velocity of the car at impact and the range. Do y'all know what the two pieces of information are? No, we assume, well, we need to know the acceleration in the y direction. Is that what you mean? Kyle, right? Yeah, okay, so we need to know that, but two other things about the car. What, Caitlin? We need to know its velocity. Did y'all catch it on there? It showed the speedometer. No, it's like 95 or something. All right, but we need to know his speed just as he hits the ramp. What else do we need to know? We need to know the angle for the projectile. So those are the only two things that we need to know. We need to know what is his initial speed, and then we also need to know what is the angle. Draw the picture, and then from that we can figure out what is the range. I'll call that x. And then I also want to know what is the velocity at the end. And for kicks, let's just say, let's go ahead and also find out what is the maximum height that he achieves. So a couple things. It's at about 95 or so right before he hit the ramp, so let's just go ahead and call it a cool 100. miles per hour. We need to convert this 1 hour, 3,600 seconds. 1 mile, 1609 meters. And that gives me 45 meters per second. So next time you're out with your friends or whatever, you're driving 100 miles an hour down Highway 1, don't do that, actually. Next time you're out driving, you can talk about the conversion between miles per hour to meters per second. All right? So our speed is 45 meters per second, and our angle is also, well, what do you think the angle is? Let's say it's 45 degrees, because that gives us what? Maximum range, yeah. So let's go with 45 degrees. It looks to be about 45 degrees. Though a 45-degree ramp is a big ramp. That's a big incline. But let's say that it is 45 degrees, and then we'll revisit it. And now I just want to know, what is his range, what is his height, and what is the speed at the end? Well, the speed at the end, you can probably tell me right off. Right? What is the speed at the end? 45 meters per second. Right, because remember this vector breaks into two pieces, Vx and Vy. Vx remains constant all the way throughout, and Vy gets smaller, goes to 0, but then increases again in the negative direction. So notice that these vectors at the end are exactly the same as these vectors at the beginning, except the y vector has just been switched. So the magnitude of the speed at the end, or the magnitude of the velocity, is going to equal to 45 meters per second. Exactly what it was at the very beginning. So really we need to know the x range and the y range. I'm going to write our equations. I'm going to write them a little bit differently this time, because I'm going to differentiate between my x and my y motion. So x is equal to Vx times t, and then also y is equal to v naught y times t plus 1/2 ay t squared. These are the same kinematics equation, except I left off this term for the x because the acceleration in the x direction is 0. And then I've also left off the little 0 here because Vx doesn't change. So Vx is the same as V naught x. With me? Yeah, okay. So my next equation, the second kinematics equation, it doesn't really mean anything here, but just that Vx is equal to V naught x. And that, I've already said that. But over here, Vy is equal to V naught y plus ay times t. So those are my kinematics equations. I'm just going to sort of leave this one off because it's obvious if you assume that the acceleration in the x direction is 0. These are exactly the same as what we had before, the same equations, except I'm just splitting them into the x and the y. And then I also need to know, on all of these, the x and y components of the velocity. So I'm going to write v naught x and v naught y here. It's going to be v naught cosine theta, v naught sine theta, 45 meters per second, cosine of 45 degrees, and that's equal to 32. And then it's going to be exactly the same here because cosine of 45 is equal to sine of 45. Alrighty? So we're almost set up to sort of start the problem. But these are all things that you'll need to figure out. You'll always need to figure out, or most of the times, you'll need to know the initial velocity in the y direction and in the x direction. So, looking at my equations, I want to know x. I know what Vx is. It's equal to 32. But I don't know t, right? I don't know t. But what is the motion that governs the time in the air? The y motion. How high it goes in the air will determine how long it's in the air. So I'm going to have to look at some of these equations over here in order to figure that out. You remember when we did the free fall problem? Threw something up in the air to find out the time that it's in the air? what do I consider? What's a trick? Not a trick, but a piece of information that I have that I need to know. The velocity at the top is equal to 0. I know it's almost 1140. Let's just write this down. So the velocity at the top is equal to 0. So I can say then that Vy at the top is equal to V naught y plus AYT, and this is equal to 0. We'll pick up with that on Monday. But y'all have a great weekend. Be safe. See you on Monday, okay?